Good afternoon, ladies and gentlemen, and welcome here to the technical forum of the group exhibit Hydrogen Fuel Cells and Batteries. We have our last presentation today, which will be quite interesting, I hope, for you. So please have a seat and have a drink on the house, coffee, tea, soft drink, whatever you like, and listen to the next presentation, which will be about in-situ characterization of single cells and their components. We have the head of department fuel cell system with us from Fraunhofer Institute for Solar Energy Systems, the ISE. So please welcome with me Ulf Groos here on stage. Yeah.
Thank you very much, Uli. Welcome all, welcome ladies and gentlemen. And yeah, as Uli said, I'd like to talk about the characterization of single cell and its components of a cell. Please let me give a short overview of my department. Fraunhofer ISE, as Ulrich said, we are situated in the very south of Germany in Freiburg, Black Forest area. Our main focus areas which we work on is characterization of cells, which I will talk about later on, and stacks with a special focus on the local effects that we have. Then we do lifetime testing, we investigate pollution effects of contamination, whether it's contamination of air or hydrogen or contamination by corrosion products. We make use of our walk-in climate chamber and we do system testing. We do also test the single components of a system, balance of plant components, and we also are in development, whether it's development of cells, stacks or systems. Fraunhofer and my department, our main business model is to assist industry. So we work very close together with companies and provide research services so that they can optimize their products. Our main motivation is to bring these fuel cells on the road. And therefore, as I said before, we provide research services to our industry partners. What I would like to focus on my talk in the next minutes is that we established a reproducible manufacturing of MEAs in order that we can provide research services for customers which develop components of an MEA. So we can then turn their components in a functional MEA and test them in situ. To test them, of course, one point is performance characterization, other point is characterization of the long-term stability. And we do not only do in situ characterization, we also make use of ex situ testing. So looking at the first point, manufacturing, as I said before, we established a method which enables us to reproducibly produce and manufacture MEAs. The idea is not to develop the best MEA in the world, but to provide research services, testing services to customers who develop electrodes, who develop membranes, who develop GDLs, and then to test them in situ, we first have to have the capability and competence to manufacture reproducible MEAs. And what you'll see here is an SEM picture of a CCM which we made, and we see a very homogeneous structure. Homogeneous structure is one point, but performance is the other point. And in this graph, you see a variation of the ionomer content indicated by the different colors. So we changed the ionomer content within an electrode, and then we made polarization curves. We produced several samples of the MEAs, and we see that for each sample, the polarization curves are matching. So this again shows that our manufacturing method gives reproducible results. This was a characterization of performance, but I'd like now to focus on characterization of degradation effects And what you see here in a lot of graphs, of course, is that we performed degradation testing, accelerated stress testing according to the testing protocols of the Department of Energy in the US. And there are different accelerated stress tests regarding on catalyst support, regarding on the catalyst itself. We performed the degradation of catalyst support 2 times. Then there are protocols for membrane, and we also did some in-situ characterization with different load cycles. So here we had a rectangular load profile which we applied to the cell, and a trapezoid load profile. We did a lot of cycles, so what you see here is that we performed this AST test up to 80,000 cycles. And we compared it in one setup, so every AST protocol was performed within the same test bench and the same test cell. So we had a very good comparison of the effects of different load profiles, different long-term test protocols. You see different graphs which show the degradation behavior regarding to certain parameters. So in this graph you see the degradation of the voltage. Here you see degradation regarding the high frequency resistance. This is the low frequency resistance. Here you have the electrochemical surface area, which degrades over time, the double layer capacity, and the crossover current. What we like is especially to investigate the performance of different electrodes is that we do impedance spectroscopy, electrochemical impedance spectroscopy, but we like to do it also in nitrogen atmosphere. If you use nitrogen atmosphere, you can have a close look at the typical so-called 45-degree arc at very high frequencies. And at one point we realized, okay, it's not a typical 45-degree performance, but it's more like an arc. It's not 45-degree, it's more like an arc. And we ask ourselves, why is this? So we created an electrical circuit model, and we specially introduced effects that might occur from the interfaces. So we introduced interface resistance from a membrane to a ionomer, and an interface capacity from membrane to the catalyst particle. And by doing so, we could then analyze the development or the dependence of the different parameters, which are shown here, on the ionomer content. And by that we realized again that the ionomer content has a great influence on these parameters, and especially these interface parameters are crucial. So by that you can learn how a certain ionomer content or a composition of your electrode affects the performance, and on the long term the degradation. For us it's very important to make use of these models, even if it's simple models like electrical circuit models, for analyzing the results and to give hints how to optimize electrodes or MEAs. So let's see if it's working for next slide, but perhaps you can help me for the next slide. Thank you very much. Another possibility which we are developing right now is this very nice and I would say worldwide unique test bench. We introduced 30 single test cells into this test bench which can be operated simultaneously. So we have a single test cell which has an active area of 4 square centimeters and can be operated under automotive conditions. So pressurized up to 1 bar, it's temperature controlled, We have humidifiers in front. And with this test bench, you have great possibilities to investigate many different materials at the same time, or one material under different operating conditions, like variation of the stoichiometry, variation of temperature, variation of humidification, variation of load profiles. And in one time, in one test bench, you get many, many results, which otherwise would make necessary a broad variety of single-cell test bench. So this is a test bench where you can test 30 single cells in parallel. At the beginning, I said that we are also doing in-situ testing of different components. So in this case, we look at the CCM within an SEM, a scanning electron microscope. And the speciality of this SEM is that's an ESEM. It means environmental scanning electron microscope. And this allows us to introduce some water in the atmosphere, so it's not a vacuum. You have some water inside, and by variation of the temperature, you can look at the three phases of the water. So gaseous water, liquid water, and then the water is freezing. And so you can apply freeze-thaw cycles to your components and look at the change of material properties, maybe the hydrophobicity. The ESIM is combined with an energy dispersive X-ray, so we can analyze the element distribution into in the sample. Secondly, we look with in-situ testing, and this special method is called Fenton tests. So we investigate the contamination effects of different cations. So it might be iron, which is especially harmful, or copper, or aluminum, or other cations. And here you see some results after doing this Fenton test with different cations. So we can investigate the chemical stability of different membranes. We also do analyze of product water, for example. We have a measurement system called ICP-MS, inductively coupled plasma mass spectroscopy, which allows you to do element analysis of liquid samples. And in this case, we collected the product water of a fuel cell stack with metallic bipolar plates, and what you see at the end is that you find a lot of iron in the product water, and as we have seen before, iron is very, very harmful to the membrane. So you should work about your metallic bipolar plate, or apply another anti-corrosion coating. In this case, we used a graphitic stack, and again we collected the product water, and again we found some amount of zinc in the product water, and also silicon. So this can allow you some optimization of your system components. If you find some harmful elements in the product water, you should think of where are they coming from and what can you do about it, so that you have a long-term stable stack and fuel cell system. Corrosion might occur in the metallic bipolar plate, so corrosion testing of metallic bipolar plates is an issue. And one method which is often applied is measuring the corrosion current after time, so we have a setup for that. And of course, the conductivity of your bipolar plate is very crucial. So we developed in-house a measurement setup for measuring the in-plane and the through-plane conductivity of metallic bipolar plates, especially the through-plane conductivity of very, very thin samples, like metallic bipolar plates with a thickness of 100 microns and below, is very tricky. So we had to develop something in-house, as it's not available commercially. So we can do also conductivity measurements or measurements of the resistivity in plane or through plane of these metallic bipolar plates or gas diffusion layers. So coming to a conclusion, I presented methods for doing in-situ testing, whether it's regarding performance or lifetime testing of complete single cells, or we are also able to manufacture our own MEAs out of customer components. Therefore, we can investigate the functionality of the different layers that you have inside a cell, and we also have methods available to do ex-situ testing of certain components within the cell. So, thank you very much for your attention. If you are interested in my last talk, so I had 4 talks altogether at this technical forum, please have a look at the website h2fc-fair.com, where you can find all the videos and have a close look after the fair on it and tell your colleagues. And last but not least, all of you, you are heartily invited to have a good cup of Freiburg roasted coffee at our booth. Our booth is right over there, C62. You're welcome. Thank you very much.
Thank you very much, Ulf, for this excellent presentation. I would like to ask you, are there any questions from your side? Then just raise your hand. I'll be with the microphone right with you. If it's not, once again, the invitation to booth number C62, where Ulf is be found today and tomorrow as well, for any questions you might have and for a closer look at the services that Fraunhofer ISE is supporting to you. So thank you very much for your attention. Thank you, Ulf, for the presentation. Once again, here's your applause.
Thank you, Ulrich. Enjoy your evening. Thanks.
Okay, that's it for today. No more presentations here on the technical forum. Some are going on in the public forum if you're still interested. So hope to see you tomorrow. Goodbye.